Professor Enrico Motta from the Open University is going to talk about exploring the dynamic of research. I mean, and I know Enrico from a long period of time, but I prefer to read a few sentences because otherwise, if I make a mistake, he will remember forever. So Enrico, I mean, with Enrico, he's the founder of the International Summer School on Ontological in Engineering and Semantic Web, started in 2003. And during 14 years, he has been the editor-in-chief in the International Journal of Human-Computer Studies. I mean, related with projects, he has a long experience in European projects, and probably the most relevant is the project already funded by the Milton Keynes City, which is Milton Keynes Smart Initiative with 17 million pounds. He's professor in knowledge technologies at the Open University, and he also holds a professional appointment at the Universidad of Bergen in Norway. So thank you, Enrico.
Okay, thank you very much for the gentle introduction and for inviting me to this great venue. So what I'm going to do today is I'll give you a little bit kind of more applied presentation than some of the ones before. So what I want to talk about is essentially to talk about what I will call kind of modern AI, something that has already been touched by previous speakers about the different kinds of AI, the kind of bottom-up machine learning-based AI versus the top-down knowledge-based AI. And in particular, show how these ideas can be applied to a very specific domain that hopefully will be relevant to everybody here. You know, understand this is quite a heterogeneous audience with some AI experts, but also people from a variety of disciplines. Of course, all of us do research, so hopefully that the kind of solutions that we have developed for research analytics may be interesting also beyond AI and computer science. So this is, yeah, I mean, of course, my talk is kind of number 9 in the list. So a lot of, some of the things that I will say have already been said probably better by previous speakers. But essentially, the key point I want to make is that is the one that has been made before, is that the explosion of big data over the past couple of days has transformed many disciplines, and in particular AI, not just AI, but also other disciplines, but in particular AI. In fact, it has been pointed out by previous speakers, you know, AI has a very fine tradition of research in knowledge-based systems, in models of problem solving, which are pretty much top-down, in which we understand the domain model, we understand the problem-solving methods, and then we try to apply this knowledge to a particular domain and a particular application. But this approach, although it was not a complete failure, it didn't really scale very much. But then, you know, during the 90s, of course, the landscape changed with the big data explosion, and this has then made possible to build a new type of AI techniques basically on bottom-up approaches, on machine learning, on exploitation of data. And the bottom line is that now AI is, you know, one of the most important strategic technologies, as we saw before, in a number of countries. So the work I'm going to talk about is essentially another big data domain, let's say medium big data. They are, you know, really incredibly massive big data domain, but this is actually quite a big data domain that is essentially the domain research. So if we look at the domain research from a sort of knowledge-based system perspective, essentially is a domain populated by people like us, populated by researchers who tend to write papers, and these papers, of course, they are situated in certain research areas. In fact, typically, for any given paper, that particular paper will be relevant to more than one research area. And of course, you can, you know, dig down even more closely into papers, and you can see the papers may propose new theories, or may propose, you know, may talk about technologies, etc. And then, of course, there is the whole ecosystem around researchers. You know, researchers work in projects, they collaborate with other researchers, they belong to organizations and countries, etc. So essentially, from the point of view of scholarly analytics, basically you can see this as really massive knowledge graph. And when I say massive, it's actually really pretty big. We currently work with, oops, it's very sensitive. Currently we work with the data provided by Microsoft Academic, and they have a basic database of about over 200 million papers and over 200 million authors. So it's pretty big space to analyze. So I won't have time to tell you all the kind of things that we've done in this domain. But basically what we are interested in doing essentially, now that we have access to this huge volume of data, what we want to do is a number of things. A, to basically examine, investigate this data, use by and large what we'll say bottom-up AI techniques, machine learning kind of techniques to really understand much better what goes on in the domain. And at the same time, as a spin-off, also produce services which may be relevant to a variety of stakeholders, other researchers like us, but also, for example, we work very closely with Springer Nature, which is one of the top 2 academic publishers in the world, and we have developed a number of systems that they use in their business, but also other government funding bodies, etc. So in particular, what I will do, I just selected two things that we have done, and I like these things because A, they've been very successful, but also there are kind of things that also are quite useful to talk about in a scenario like this to explain a little bit more in practice how AI works these days. So the first thing I'm going to talk about is now a little bit old. The first version of this algorithm was developed in 2012. And it basically addresses a problem which is particularly important in computer science, or let's say particularly dramatic in computer science, but is also relevant to every single other research area. For any given area, for example, computer science, it's actually quite useful to have a kind of knowledge map. It's actually quite useful to know what are the areas of practice in computer science. It's a little bit like the International Classification of Disease, the ICD. If a disease is not there, it's kind of a problem if you have that disease. And so if you work on some research area and that research area is not in the official catalog, so I really need, this is the most sensitive device I've ever, you just think about it and it changes slides. So I really need to be careful with my left thumb here. Cognitive technology. Yeah, in fact, the next thing will be somebody gives the talk, the AI system will give the talk instead of me. So what this means in practice, well, if we concentrate on computer science, which is, of course, my area of research, the standard we have to tell us what are the research areas in computer science is the ACM classification, which is actually not very good. I mean, I say with all the love in the world to ACM and the people who produce it, is a standard that is developed manually, and it takes a really long time to come up with the list of research areas. In fact, there's been 14 years gap between the 2 releases, and of course, you don't need to be a computer science expert to understand that in those 14 years, lots of things happen, so that by the time the new catalog, the new taxonomy of research areas is released, is already obsolete. The other problem that is a little bit kind of more fundamental is that this basically taxonomy reflects the views of the experts that produce it. And of course, I'm sure that if all of us decide to sit down together and agree on a taxonomy of AI research areas, it will not be very easy to agree. My area is a super area of your area. No, your area is a super area of my area, etc. But the other thing is that from a practical point of view, because it's produced manually, it only contains 1,000 research areas that, according to our estimate, is about 1/10 of the number of research areas in computer science. And for example, if we focus on AI, which is the topic for today, the ACM classification only has 84 topics. Our analysis shows that there are about 1,800 topics in the AI area. So the problem, apart from all the ideology, etc., the problem practically is not very useful. If I want to understand what goes on in research, I don't want to know what goes on in AI. I want to know what goes on well inside AI. If I hire a PhD student, I don't tell the PhD student, say, your PhD is in AI. Typically, your PhD will be in a very specific, very granular research area. So essentially, the first thing we did when we started working on scholarly analytics about 8 years ago was to try and tackle this problem, to come up with a taxonomy of computer science that was accurate, comprehensive, and granular, so that then this could provide essentially the fine-grained handle that we will need to do everything else, for example, to explore the dynamics of the area. So again, I understand this is quite, a heterogeneous audience, so I won't go into too many technical details. But basically, I want to, again, relating to some of the presentation we had before, I would like to give you an idea of the style of, ways in which we build AI systems nowadays. Essentially, so we start from very big data. Our corpus of computer science data is in the millions. It's not all the 200 millions that Microsoft Academic provides, but it's several millions. And of course, you don't really know how many of those millions, in those millions of papers, how many are really computer science, because of course, papers are really hybrid. We talked about AI and medicine. Some papers may have, 80% medicine, 20% AI. Some papers may have 90% AI and 10% medicine. So it's quite an interesting domain to navigate. But essentially, what you need to do, obviously, if you want to come up with a new taxonomy or research areas in computer science, essentially to do two things: to identify what are the topics, and then crucially, because you don't just want a flat catalog, to understand the relations between topics. So this is exactly what Klink algorithm does. He uses a mix of machine learning and external knowledge bases to decide with a certain degree of confidence what is a topic in computer science. And again, this is something that a number of speakers earlier talked about the fact that there is this pendulum swings between sort of machine learning, behavior-based AI, and knowledge-based AI. And reality, you need both. And this is really a nice example in which you really need both. And then basically use again the same, we also use different machine learning techniques, use the same generic schema that is a combination of machine learning and external knowledge bases to decide what are the relation between topics. So just to give a very simple example that hopefully everybody who could relate to is, let's look at problem number one, that is deciding whether something is a research area or is not a research area. Basically, if you look at all the metadata associated with an article, there is abstract title, there is, of course, authors. People normally, most publishers will ask people to put keywords, to annotate their papers with keywords. And for example, typically, a subset of those keywords will be research areas, a subset of those keywords will not be research areas. Now, the interesting thing, and this is where the big data element becomes really important. The interesting thing is that if you have millions of papers, you will find a kind of statistical fingerprint for any given area. Let's say semantic web. Semantic web will have quite a lot of correlations with a relatively small number of other areas, and then there will be this kind of gentle degradation. And this is something that Klink uses to say, this looks like, statistically, this looks like a research area. I don't really, in terms of knowing, in terms of real understanding, Klink doesn't really know anything about research areas, but he knows that something that looks like this over a corpus of millions of papers might be a research area. Well, in fact, there's something like, for example, a typical keyword that you find in papers may be like case study. Now, case study, I will argue, is not a research area. So if you look at the statistical fingerprint of case study, it would be much flatter than that one. It will have a lot of correlation with a lot of areas rather than just this kind of graceful degradation. But the interesting thing is that, of course, this only gets you to about 70% F-measure-based, 70% precision accuracy. So what is a knowledge-based approach in this case? Knowledge-based approach means that Clink is able to decide whether, what is the level of confidence he has in a particular decision. This is a topic, this is not a topic. And when the level of confidence is below a certain threshold, of course, what do? You can just use the the huge amount of knowledge that you find on the web to validate, to confirm or not confirm what the statistic tells you. So, for example, if something, is something like semantic web, Clink thinks that is a research area, but is unclear statistically. Well, certainly, if there is, if semantic web is a research area, there will be a conference on the semantic web. It will be a topic in call for papers, etc. So, this is something that you can do, and this is related to what Frank was saying earlier, that. Clink, at least in the earlier version, not the one we are building at the moment, was not very good at explaining why things were deduced. But of course, if you then integrate Clink with a knowledge-based component, then at least you have a much better explanation mechanism. And this, I will say, is kind of generic architecture in which you have a big data phenomenon. If you have a big data phenomenon with lots and lots of data, you cannot use knowledge-based systems. You need to have, the statistic, the machine learning methods to sort of build, to be able to manage that, to be able to manage the data and extract patterns. But the problem, as I said, as some of the earlier speakers have pointed out, that simply detecting structures and regularities in big data is not enough. In particular, it's not enough for explanation point of view, but very often, like in the examples that I showed before, is also not enough from a performance point of view. So basically, what I will argue is that a good generic schema for AI techniques is the one that integrates these two elements. And indeed, we use these in a number of our solution in scholarly data. But for example, we also work on robotics, and our recent work in robotics shows that if you not only use, for example, deep learning for object recognition, but you augment the architecture with external resources, for example, like ConceptNet or Visual Genome, essentially resources that give you a little bit of common sense knowledge, then the accuracy in object recognition improves. But the nice thing about this is also that the availability, essentially, of high quality knowledge bases, large-scale knowledge bases, in particular common sense knowledge base, has been a dream of AI for at least 50 years. Indeed, the largest, the longest running project in AI is Psych, that started in 1984, and is, I understand, is still running. Or at least Doug Leonard is still a Psych op, and they still use Psych. And of course, that was the problem with Psych was that it was manual. But the nice thing is that all the developments in machine learning, information extraction, in computational linguistics, etc., of the past 30 years now allow us to build automatically or semi-automatically these large-scale resources that then you need in order to make sense of machine learning-based AI. So I think there is a nice sort of, I would say, incestuous relations between all these components. Okay, so that was the more AI, let's say theoretical AI, or kind of man of the street theoretical AI part of the talk. So the rest is a little bit about outputs. So essentially, what we did was to apply Clink on a very large corpus of computer science papers, and we generated these what we call the computer science ontology, which is the largest resource of this kind in the world, has 14,000 topics and about 160,000 semantic relationships. And just to give you an idea, under artificial intelligence, as I mentioned before, there are 1,800 subtopics in our graph. This has been quite successful and is now being adopted by Springer and Nature for their own classification. The thing is that, of course, the ontology is completely useless unless you have tools that use the ontology. So the first thing that, of course, a key thing that we need is a way to do automatic classification of papers, so that if you remember that knowledge graph I showed you at the beginning, what you want is to know for each paper in which research areas the paper is situated. So we have built something called the CSO classifier that I don't know whether Roberto is still here, but he might be happy to know that he uses word embeddings. That is what he was really keen on. He used a combination of basically syntactic and semantic analysis of a paper. And therefore, you run these on millions of computer science papers, and then you get a very, very, very accurate and fine-grained view of what goes on in that area. And incidentally, for those of you who are computer scientists, there is a free service. You can go to our website, you upload your paper, your abstract, whatever you want, and you will do the automatic classification for you. And 5 minutes, okay. So a version of this auto classifier is now being deployed at Springer, and basically all the computer science proceedings that Springer published are now automatically annotated using our tool. And the nice thing, and this is a nice example about how academic research then really can add value to industry. Basically, we have calculated that basically about 9 million, because of course the accuracy is so much higher for a problem like this when you have to. One thing is to generate metadata for the papers. Although we have actually quite a bit of evidence that even for single papers, even authors make mistakes in annotating their own papers. And if you talk to the editors about Elsevier Springer, they will confirm that. If you annotate proceedings, a proceeding may have 80 papers, may have 150 papers, or large conferences. It's very, very difficult for a human being to manage that complexity and generate the correct metadata. So by using this tool, they get a much, much better accuracy, and therefore they get much better value. Okay, there was one other thing. How many minutes have I got? There was one other thing that I wanted to... 4 minutes, yeah, that's more than enough. Okay, so the second thing that I wanted to show you, because I imagine that regardless of which background you come from, whether you're a computer scientist or biologist here, you are all an epistemologist. So I guess who knows about Thomas Kuhn? And yeah, quite a few people. Not everybody, but quite a few people nod. Okay. So the thing about Thomas Kuhn is in his incredibly successful book. He basically says that interesting things happen in science when there is some kind of crisis, when there is a paradigm shift, and when essentially the current theories, the current paradigms don't really adequately explain the current world. So of course, as I mentioned before, now we have this huge knowledge graph. We know everything that anybody ever publishes. So we thought, can we operationalize Kuhn? Can we sort of, by analyzing this graph, can we predict when something new is going to happen? And of course, this was a completely crazy idea. But again, many thanks to Springer Nature for funding a PhD research on this topic, which seems a little bit crazy to start with. But in reality, if you start thinking about it, it's not so crazy. Essentially, the analogy is the one, I'm not a volcanologist, I'm not a geologist, but I understand that in contrast with earthquakes, which are quite difficult to predict, volcanologists are actually pretty good at predicting eruptions. And this is what they do. They are very good at reading the signs underneath the volcano, essentially the seismology, the geology, etc. And from that, they can say, hey, this volcano is about to erupt. You better get out of here. So we thought, okay, if we essentially, at any moment, let's say right now at whatever it is, 4:30, we have a certain knowledge graph. And then next year, we will have a different knowledge graph because more papers will be published. And then more papers will be published in different areas. So we thought, if we have the methods to analyze the difference between these knowledge graphs, can we tell that something big is about to happen because we notice differences? And essentially, if I can, I must say the most difficult thing about this talk is to manage this incredibly sensitive device here. So essentially, we hypothesized that when, consistent with, this is a little bit liberal interpretation of Kuhn, but basically we thought, okay, so maybe what really happens is when there is when a new area is about to emerge, something changes in the dynamics of the areas which are close to the new area. That was our hypothesis. So which is wonderfully visualized in this slide here, which shows essentially you have these 3 areas. And when you talk about areas, also you talk about communities. These are the people, essentially, these are 3 communities of people. And you can see a year N, they don't really collaborate very much together. And then a year N plus 1, suddenly there's been a massive increase in collaboration. So we thought, maybe that is a sign something interesting is happening. And indeed, lo and behold, we did an empirical analysis of a substantial subset of of computer science, and we found that indeed the pace of collaboration associated with debutant topics. Is there anybody from England in this place? Debutant. So I could remember how to pronounce debutant. The pace of collaboration for debutant topics is consistently higher than for non-debutant topics. So that means, for example, if the new area called, semantic web is about to happen, the areas close to the semantic web, for example, knowledge representation, web, agents, etc., will show over, if you do an analysis over a couple of years, 2, 3, 4 years, a dramatic increase in the pace of collaboration. So, this exactly was the first part of the PhD. And the second part of the PhD, once this was proven, was actually to find a computational way to actually do it, which took 2 years to find an algorithm that could actually manage the complexity. So I will skip the technical details also because I think nobody really probably cares about the technical details. But I will just give you an example. So essentially what this algorithm is able to do with an accuracy of about 77 to 80% to predict the emergence of a new area before the area has emerged, because otherwise it will not be too difficult to predict. And of course, the interesting thing is that, so what is the output? Because of course, because the area has no emerged, we cannot tell you what is the area. But what we can do, we can tell you what is the space in the network where something interesting is really happening. We can tell you which are the interesting papers, and we can tell you which are the interesting authors. So the idea is that essentially this information goes to a domain expert, for example, an editor in a publishing company which deals with this area, and that editor, will look at the papers, will look at the information we provide through Algo, and say, something interesting is happening here. Okay, so I will stop here. If you're interested in our group, that's the URL for the website. Scholarly knowledge mining is one of the key areas in which we work, but we do also other things in particular digital humanities and robotics, which might be of interest to some of you. Thank you very much.
Okay, thank you, Enrico. So we have time for 5 minutes, more or less. So I will start, and then.
Hi, Enrico. Thank you for your talk. So I understood that you use the abstract of a research paper to classify them.
Yeah.
So what are the challenges that emerge, and how the classification can vary if you use the full text of the papers?
Sorry, these things continues. We tend not to do we tend not use the full text for the topic classification. We use the full text for other things. For example, if you want to understand, as I mentioned in my example, which technologies the paper talks about, then you really have to analyze the full text. But basically, what we found is that if you want to classify a paper, typically within a certain, with a certain accuracy, which is always in the sort of way. For the classification, actually, we are close to 90%. With a certain accuracy, all the information you need is either in the title or in the abstract or in the metadata or in the other metadata. So if you start, if you add the text, then first of all, it becomes computationally much more expensive. And if you then use methods which are computationally not too expensive, the noise is too much. So the accuracy goes down. So for classification, we just need, we just use the abstract and the metadata primarily, and the title.
One reason we need this taxonomy, whenever I submit a paper, I'm supposed to provide keywords. I'm supposed to classify the paper.
Yeah.
why should I do that? I think by now they should be able to classify the paper without me choosing the topics, right?
In fact, yeah. If you send me your paper, I'll classify it for you. I will classify your paper for you. Absolutely.
Yeah. So I think we should just stop classifying papers.
Well, that's well, hopefully. I mean, that's beyond my call. But if let's say if our commercial partners get their act together very soon, certainly for a subset of publications, you will use our classifier to classify your paper. Yeah, it will be integrated with the submission process. But of course, we want you to check. I mean, we don't want you to trust us. Yes.
Thank you very much. Very nice and interesting talk. One comment and one question. The first is the comment. I'm in the field of material science. And what is emerging now in the community is the tendency in parallel with the automatization of calculations posted in a repository is to go into the PDF of the 50 million plus papers in material science since scholarly articles are written, and to extract from there, and this IBM is very much on the forefront, extract their materials data. And this is really shows how also in other fields this type of classification and extraction out of the PDF is very, very important. And it's crazy that we are still writing paper in a sort of a freestyle, and we are not forced by editors to fill some metadata that eventually could also help, because it's very tough to extract figure nowadays. I mean, if you read a paper, it's very easy, but for computers, it's still difficult to extract figures and classify in the right context. This was the comment. The question is more related to the emergence of bibliometrics, also to determine careers. I'm working in Germany, but I'm originally from Italy, where this hysteria related to ANVUR is really permeating everything in the academic system. And we know that, you know, there were in Nature papers that the Italians are the most cited researchers in the world, and really this bibliometrics push forced people to really take the issue very seriously. But it's also true that things are not without fraud.
True.
And let's take the case of huge Hirsch index colleagues, also from the Asian countries, that are based on triangulations of citation systems. So now the question is your system able to extract or to detrend and purify a high index, or you name the index, based on the fact that some authority is also based on the citation network, or we are still too much in a smoky area, and this type of work is too difficult, possibly, or probably not remunerative.
So, yeah, if I understand correctly your question, what you say is that is it possible to analyze the citation network in such a way that you detect these kind of triangulations?
Yes. Because I mean, if you, for computer science, cite my papers, and I cite papers of economics, and we close the circle because citations are very cheap, not really checked. There is no ontology, not deontology in citing. I mean, human being can do it, but then people don't do anything else. But this could be also easily detectable by computer, whether the citation is really mature, is really there, is a courtesy citation, or whether it's like a sort of system of pushing together people. Yeah.
No, this is a very good. So yeah, I mean, we have not done this. So also because, to be honest, I, for the reasons actually that you expressed, in contrast to other people working in this area, I really like to stay away from bibliometrics. I don't want to become the most hated researcher in computer science by people. You know, I don't want to put service online that tells that Enrico Motta is really a complete crap researcher compared to somebody else, compared to us and Gomez Perez. So okay, so essentially there are two. I'll try to be very quick. There are two interesting things that you suggested, which actually I will write down, and then you know, that will be my next proposal for next year. There's one thing is essentially almost like a topological analysis of triangulation. Yeah, that, to be honest, I don't see any difficulty. I mean, it certainly is an infinitely easier task than trying to detect these patterns, you know, associated with the Kuhnian revolutions, let's say. So that is very, very doable, and you know, if there is interest, is certainly something that we'll be very happy to do. The other thing is, I think, is a little bit more subtle, because what you're also talking about is some citations which are just there to increase number of citations. Okay, so in order to do that, you need to go inside the paper. It's not just looking at the topology, you know, at the topology of the network, but looking inside the paper. That we are not working specifically on that. We are working on essentially knowledge graph creation, automatic knowledge graph creation from scientific papers. As part of that, I think it would be quite interesting to look at that. There is some work by somebody called Simone Teufel. She did some work on, you know, on the epistemology, on the claims, blah, blah. I think a lot of that can be operationalized, especially if you are not trying to understand the whole narrative, you know, epistemological narrative of a paper, but you just try to understand, okay, is this really important reference or not? That, I think, can be done reasonably easy.
Very shortly. This is really something that publishers are hungry of. I mean, I'm academic editor in certain journals, and in the end, the editor-in-chief are picking references, etc., based on really on nose, but the nose has a limit when the volume of paper is increasing so much, and people are now following in Wiley this Dimension.ai, a new company from the UK that is doing.
Yeah, actually, they also have adopted our ontology.
Okay.
You work very close with them.
Very good.
Thank you, Enrico.
Thank you very much. That was great.